Welcome to Brain Vision.
Okay, so for the first question, we can set out the energy balance equation for the refrigerants, which is E dot N equal to E dot L. If we expand it, we have M dot R H1 plus Q dot N is equal to M dot R H2. So M dot R here is the mass flow rate for the refrigerants, and H1 is the initial enthalpy for the refrigerants. And Q dot N here is the heat that was absorbed from the air, and H2 here is the final enthalpy for the refrigerants. If we do some arrangement here, we have Q dot N is equal to M dot R times H2 minus H1. So we know the mass flow rate for the refrigerants, which is M dot R here, can be equal to the initial volume flow rates of the refrigerants over the specific volume at the inlet, okay? Which is equal to 2.65 liter per hour over 0.0253 meter cube per kilogram. If we convert the units liter per hour to meter cube per second, so eventually we'll have the mass flow rate for the refrigerants is about 2.91 times 10 to the power negative 5 kilogram per second. And we know the initial enthalpy for the refrigerants is 220.2 kilojoule per kilogram, and the final enthalpy for the refrigerants is 398.0 kilojoule per kilogram. So now let's plug in back to the equation to determine the rate of heat that was absorbed from the air, which is equal to 2.91 times 10 to the power of negative 5 kilogram per second multiplied by 398.0 kilojoule per kilogram minus 220.2 kilojoule per kilogram. And this will give us the rate of heat transfer from the air should be equal to 5.174 kilowatts. I'm sorry, no. I forgot something. Times 10 to the power of negative 3 kilowatts. Okay, which is equal to 5.174 watts. So now we figure out the rate of the heat that was absorbed from the air, which means that the air was losing the heat at 5.174 joule per second. Okay, so therefore we have the absolute value or the magnitude of the rate of heat transfer out of the air is equal to the rate of heat transferred to the refrigerants, which is the rate of heat absorbed from the air by the refrigerants, according to energy conservation law. Okay, so we have Q dot R is equal to Q dot N, which is equal to 5.174 watts. So we have absolute value Q dot R is equal to M dot A times Cp times delta TA. M dot A here is the mass flow rate of the air. Cp is the specific heat for the air, and delta TA is the changing temperature of the air we're looking for to determine. If we do some arrangement here, we have delta TA is equal to Q dot R over M dot A times Cp. We know the mass flow rate for the air is 0.75 kilogram per second, and the specific heat for the air is 1005 joule per kilogram times degree Celsius. So therefore, let's plug in back to the equation to determine the temperature change of the air, which is equal to 5.174 watts over 0.75 kilogram per second, and then multiplied by 1005 joule per kilogram times degree Celsius. And this will give us the temperature change is about 6.86 times 10 to the power of negative 3 degrees Celsius. And these are the answers for this question.